minus 1 times a negative 795.8. Anybody know what that is? 540, 167. Oh, sorry. So you got 2 times 167.16, so that's 334, 542, 876.8 minus 700. You got approximately negative 80 kilojoules per mole. Let's talk about what this means for a second. The negative formation enthalpy of calcium chloride means that if you take pure calcium metal and Cl2 gas, the reference states of calcium and chlorine, and you go to form a calcium chloride salt out of them, you're going to release 795.8 kilojoules. That is because of the potential energies of those atoms with respect to one another. Well, actually, that's not exactly true. There's the potential energies of the electrons in their orbitals as well. But also it's the binding energy in the solid. You take calcium metal, pure calcium, and you ionize it and you allow it to become aqueous phase, you're going to get a release of energy, a release of enthalpy, a negative delta H, 542.83. So what that means is that those interactions between the calcium atoms and the water molecules are favorable and they lower the energy. There's an energy released when that calcium ion, goes into solution. Similarly, there's an energy associated with the chlorine ion being dissolved in solution. You take the differences between these two things, you find out that the net result is a lowering of those potentials, or a lowering of the enthalpy, a release of 80 kilojoules per mole. It's an exothermic process.
So on the test, the numbers on the right side, those would be given as part of the problem?
Yep, you'll be given all of those numbers. All you have to do is go in and do the calculation. Let's do some more problems.
How is the structure of the question going to be like?
Can't tell you. You'll find out in a week and a half. All right. So up here, I said that you have to worry about the kinetic and the potential energies of the electrons and the orbitals. Binding energy of the electrons and their orbitals becomes very important. To illustrate this, we're going to look at what's called a bond enthalpy problem. The problem we'll look at is this one. We're going to take a methanol molecule and we're going to combust it. Now, you should know after a Gen Chem class that combustion reactions are highly exothermic. This largely has to do with oxygen. Oxygen, O2, is very electron hungry. It doesn't have all of the electrons it wants, and when it goes in and it reacts with something, it pulls those electrons into lower potential energy orbitals. And so the energy in the electron orbitals decreases when an electron moves onto an oxygen. We're going to kind of look at that in a little bit more depth. Let's take this reaction, H3COH in the gas phase, plus 1.5 O2 in the gas phase, goes to 1 CO2 in the gas phase, plus 2 H2Os in the gas phase. Now, if you go look up the formation enthalpies of these guys, you're going to find that for H2O, right there, it's negative 241.8. For CO2, this guy is negative 393.51 for its delta H formation. O2 is elemental form of oxygen, so it has 0 H naught of formation. And this methanol guy right there, this is negative 200.66. It's kilojoules per mole. These are the formation enthalpies. So you could do a quick calculation, and you could say delta H of the reaction is equal to 2 times negative 241.8, which accounts for the water. So that's your H2O. Plus 1 times negative 393.5, which is your CO2, minus 1 times negative 200.66 plus 1 times 0. So this guy, the 200.66 was your methanol, and the 0 was your O2. So just do the same exact calculation. Or sorry, it's 1.5 times O2. Run that calculation and you calculate delta H of the reaction is equal to something like negative 676 kilojoules per mole. So we know from this that energy is going to be released. There is a way for this kind of reaction to approximate the enthalpy change of the reaction using bond enthalpies. And here's the gist of it. With this reaction that I've shown you, all of these species exist in the gas phase. What that means is that you don't have to worry about the potential energies of these atoms and molecules with respect to one another. I guess they're all molecules. When you don't have to worry about a lowering of electric potential when a CO2 product molecule and an H2O product molecule get together, because in the gas phase they don't get together. They're spread so far apart that you don't get any lowering of energy due to interaction of condensed phases. And so what that means is that the change in energy for this reaction is largely a function of the bonding and energies of the electrons in their orbitals. So up here I said we got to worry about the kinetic and potential energy of electrons in their orbitals. Well, the only things that change in this reaction, the only interactions that change are the interactions of the electrons in the orbitals that they're housed in. And so with this kind of a reaction, we can calculate delta H using the energies of all of the bonds, because those are the only things that change. Here's how this works. First you have to have your notes so that you can put together your bond energies. What page is that on? Oh, there it is. Your reactant molecules, methanol and oxygen, before they can become product molecules, you got to break all the bonds. A methanol molecule looks like this. It's a carbon with 3 carbon-hydrogen bonds. There's a carbon-oxygen bond between the carbon and the oxygen, and there's an oxygen-hydrogen bond between the oxygen and the hydrogen that sits on its alpha bond. In your O2 molecule, you've got 2 oxygens that are bound together by a double bond, an oxygen-oxygen double bond, 1.5 of these. In your CO2 molecule, product molecule, you've got a carbon with 2 carbon-oxygen double bonds. And in your H2O molecule, you've got an oxygen with 2 oxygen-hydrogen bonds. And so imagine for a second that we want to get from here, the reactants, to here, the products. Well, in order to do that, we're going to have to break all of the bonds in the reactants. This is going to cost us energy because you've got those bonds that are formed when the atoms came together and lowered their electric potentials. Electric potential, kinetic energy, etc. but you've got a lowering of energy when the bond forms. Therefore, in order to break the bond, you have to spend energy. Well, they give the bond enthalpy of a CH bond as 413 kilojoules per mole. Bond energy, kilojoules per mole. A carbon-oxygen bond has, where is that guy? 358 kilojoules per mole. An oxygen-hydrogen bond is 463 kilojoules per mole, and an oxygen-oxygen double bond is 495 kilojoules per mole. Every single one of these bonds has to be broken. And so there's going to be an energy investment. We're going to call it energy in, or energy to break bonds. We've got 3 CH bonds, so that's 3 times 413 kilojoules per mole. We have 1 carbon-oxygen bond. That guy is going to be 358 kilojoules per mole. 1 carbon-oxygen bond has to be broken. You've got 1 oxygen-hydrogen bond. So this guy, we said, is 463 kilojoules per mole. And then you got 1.5 oxygen-oxygen double bonds. So that's 1.5 times 495. This is energy that has to be spent to break all of the bonds that need to be broken in the reactant molecules. You add it all together, you're going to find out that it's plus 2802.5. That is just kinetic and potential energies of electrons in the orbitals, mostly. These are average bond enthalpies. So now we're going to go back and we're going to calculate how much energy is released when new bonds form. Get a different color for that. Maybe I'll use the same color. We got to form 2 carbon-oxygen double bonds, and a carbon double bond oxygen, the bond enthalpy for that guy is given as 743 kilojoules per mole. And you got to make, what are we making? A bunch of OH bonds. There's 4 OH bonds, and we said that all of those OH bonds were, what did I say, 463 kilojoules per mole. So we'll do a sum here of energy released. We've got 2 carbon double bond oxygen bonds, so this is going to be 2 times 743, but this time we're going to stick a negative sign in front of it because when bonds form, energy is released. And so the delta H will be negative because energy is being released by the system in the formation of those bonds. We've got 4 oxygen-hydrogen double bonds, or not oxygen-hydrogen double bonds, but single bonds. So 4 OH bonds. We said that was 463 for those OH bonds, and we're going to put a negative in front of that because, again, bond formation results in a release of energy. We sum those guys together, 2 times 743, 4 times 463, and we're going to get a number that is approximately negative 3,338 kilojoules per mole. Now, something I should mention real quick here is that these bond enthalpies that I'm using, they're average bond enthalpies. So they're not actually the bond enthalpies, the exact bond enthalpies in the reactant product molecules that we're looking at. They're bond enthalpies that are averaged across many different kinds of carbon, oxygen single bonds or oxygen hydrogen single bonds. And so we're not going to get the same exact number, that we got up here for the delta H of the reaction, but we're going to get a similar number. So delta bond energy is going to be positive 2802 plus a negative 3338, which is about negative 535, which is a number that's similar in magnitude to what we caught just from looking at the formation energies of the actual molecules. And so the take-home message here is that your delta H is a function of raising or lowering of these, in this case, electric potentials in the molecules. Does that make sense? If you undergo a process that requires a net input of energy, you're going to have a positive delta H. This is an indication that energy needs to be supplied from the surroundings to the system in order to drive the process. If you have a process that results in a net release of energy, a lowering of energy, this is going to be a negative delta H. This is an indication that energy has left the system. So energy can be gained in the case of a positive delta H. Energy can be released in the case of a negative delta H. But it's all a function of adding up all of the kinetic and potential energies in the reactants and comparing them to the kinetic and potential energies in the products. Then you got to account for pressure, volume, expansion. So to calculate delta H, you need to look at how energy changes. The internal energy in the system, any expansion work or compression work that's been done in the process. Once you've added all of those things up, you can figure out how much energy is required from the surroundings or how much energy is dumped into the surroundings, and you'll know something about spontaneity of the reaction. All right? All right, I think we're done.